I chewed you out.
It's cold.
It is a little bit cold. I agree. I like it cold though, so I'm happy. Sorry.
Yeah, but it was like from this morning to like now.
It's
like,
dropped, yeah.
Yeah.
It's supposed to be done almost freezing.
Yeah.
I'm
Crazy.
gonna throw my backpack
Yeah.
right now.
I hope it doesn't do that before I do
What questions do you have? Do you have questions?
I just wanted to wash my sheets. Wash them once a week.
Oh yeah, we're gonna do more examples today. Oh yeah, absolutely. Yep. Because there's even there's questions on homework that we haven't talked about how to do yet. Right?
Yes.
My marked up ones. Oh goodness. If I were organized, it'd be amazing.
It's a lot of work, but
What's that?
so it's a lot of work, but
Yeah, this will be a lot. It's a lot of work being organized. Yes. All right. So last time we talked about the uniform distribution. Remember your uniform. Yeah. You might want to actually have that on, right?
Sorry, my fault.
There it is. Well, thank you. I would have written pages if you hadn't told me. I wouldn't have figured it out until you told me.
So we got it.
Then I didn't have the projector on.
Oh.
Like I literally would not have figured it out. Did you get it, Grace? Oh, good. All right. So remember when we say that x is uniform on the interval from a to b, this is the notation that's used in the book and used in a lot of different books besides just our textbook. So this tells us that we have a certain PDF. We have 1 over b minus a, and the only x values, the support for this is from a to b. From this, remember, we also can talk about getting the cumulative distribution. But this is all stuff that we did last time, just kind of reviewing. Oops. Did that backwards. We know that for the cumulative distribution function, we don't accumulate any probability until we hit A. Then it goes up linearly between A and B. And then we hit 1 when we get to B. Now remember again, the cumulative distribution function, you can calculate probabilities from it, but it's not the same as the PDF, right? It's when you write down f of some number, whatever that happens to be, I'll say m for lack of a better letter. This is the probability that your x is less than or equal to m. So you can calculate probabilities using your cumulative distribution function, if you have it, right? To get it, of course, most times we're going to have to integrate the PDF. But in general, if you've got the cumulative distribution function, you can calculate probabilities that way. One of the things that what's nice about this is, of course, that you can calculate intervals pretty easily. Let's say that your x, and this is, by the way, this is true for any cumulative distribution function, especially the ones that we're doing for continuous distributions is where we're more interested in the cumulative distribution function anyway. But we can do this as long as we have a cumulative distribution function, we can calculate probabilities in this fashion. If I want the probability that x is between m and n, what do you think you would do? In terms of the cumulative distribution function, what do you think you would do? Well, if this isn't here, what would I write? It goes from negative infinity up to n, right? And so in terms of the cumulative distribution function, what would I write down? It's above my hand. What would I write down?
X is less than.
So if x is less than or equal to n, So what I write down?
Probability that X.
Just in terms of the actual using the name for the cumulative distribution function, what I write down? What's literally above my hand? Oh, f of n. Yeah, there you go. It would be f of n, right? It's like it was literally right above my hand. Okay? But this gives me everything n and below, right?
Yes.
Right? So if I wanted to, I need to subtract something off, don't I? What do I need to subtract off? F of m, everything below m. Now this does require continuous distribution here, by the way. The reason why we have to have continuous distribution and not discrete is because technically this is equal to the probability that x is less than or equal to n minus the probability that x is less than m, right? Strictly less than m, correct? I don't want to subtract off when it's equal to m here, correct? If I'm writing out this in this fashion. Now for continuous, does it matter if I have an equal to sign here or not?
No.
No. Okay, so for continuous, I can do it this way. For discrete, I have to be careful because you might have a non-zero probability that you're actually equal to the value. Okay? So this would be literally just subtracting it off using your properties of probability. This specifically is true for continuous distributions. Okay. I mean, you get a similar result for discrete. You just have to plug in the number right below m that goes into your support. All right. Anyway, the other things we did with this, I think we did it quickly at the end of class last time, that the mean was a plus b over 2, and the variance is b minus a squared over 12.
Is this for exponential?
No, this is still for uniform. We haven't done exponential yet. I don't know what exponential means yet because I haven't talked about it. Okay? All right. Pardon me. Okay. So, let's talk about exponential. If you have any problems with uniform, they're stated pretty simply because you have to use that particular formula to get at it. So let's talk about exponential where it's a little bit more interesting. So to get at the exponential, we're going to let, we'll say W, be the waiting time until the first occurrence of whatever observation, I should say first occurrence of, well, whatever. It doesn't matter what it is. First occurrence of, I don't know what I want to use. What word I want to even use. I'll say a success, just for lack of a better word. Of a Poisson process. Oops, spelled the word process correctly. I got stuck mid-sentence and I couldn't think of what word I wanted to use, so I'll just use success. Remember when we did Poisson process, we said that things come in at a discrete things that come in. You can't have two things come in at the same time. So you can slice up the time interval small enough into where there's at most one occurrence during each of those time intervals. So what I'm saying is when the occurrence happened, that would be a success. Right? So we're just trying to figure out when the first occurrence happened. The waiting time until then. Now, with Poisson, remember we had something like an average of 3 per hour or 5 per day or something like that, right? You agree? So that was, and we said that the number of occurrences was discrete, right? You have no occurrences or one occurrence or two occurrences. But if you're doing waiting time is continuous, right? When that first occurrence comes in, it might come in at 37 minutes, or 23 minutes, or 45.2 minutes, right? Or 5 minutes and 13 seconds, right? Time is infinitely divisible. So the waiting time will be a continuous random variable. So we're interested in figuring out what the distribution of this particular variable is. So one of the ways that we can figure out one of the reasons why we call them continuous distributions is because their cumulative distribution functions are continuous, right? So one of the main, we haven't talked about doing this yet, but we're going to talk about doing this more as we go through the semester. One of the ways that you can attack finding a PDF is to find the CDF first and then take a derivative. We talked about that last time, right? The relationship between the cumulative distribution function and the probability density function is the derivative, right? The derivative of the cumulative is the probability density function, right? Okay. So one of our plans of attack for finding a PDF is to find a CDF first and then take a derivative. So in this particular case, what we're going to need to do is we're going to look at our CDF. I'll say capital F of W. By definition, this is the probability that capital W is less than or equal to little w. All right, so thinking about it this way, we are looking at trying to find the probability that the first occurrence happened sometime before little w. I just don't know when that is yet, right? But it says the first occurrence. It doesn't tell me how many occurrences, right? I could have had 7 occurrences that happened, correct? If I wanted to know, say I wanted the probability that the first occurrence was less than or equal to 8, for example. Okay? Well, there might have been only 1 between 0 and 8, but there might have been 17 between 0 and 8, right? I just don't know how many there are. Correct? So I want to rephrase this into a question where I might be able to actually answer something. And looking at the complement, oops. If I look at the complement, that's the probability, or 1 minus the probability that W is capital W is greater than, strictly greater than little w. So the probability that capital W is strictly greater than little w means that we didn't have any occurrences at all up until W, right? If the waiting time is bigger than little w, then we had no occurrences in that first time interval from 0 to w. Right? We agree? If the first one happened write it this way with actual numbers. If w is 5, and I said probability that capital W is greater than 5, that means there were no occurrences between 0 and 5. Right? We agree? Okay? So to write that down in words, this is 1 minus the probability that we had no occurrences in the interval from 0 to little w. Right? Now, remember that W is trying to W is calculating the waiting time until first occurrence, right? But the underlying process is a Poisson process, right? The underlying theme here is a Poisson idea, okay? So this probability that we want to calculate here, that there's no occurrences in the interval from 0 to W, is a Poisson probability, right? So if lambda is your mean for a unit time interval, so we have lambda occurrences per time interval, so again using numbers. If I have 5 occurrences per hour, and W is the length of the time interval that I'm interested in, W is the number of hours, what would I use for the new lambda for the process then? If it's 5 per hour and I have W hours, what do I do by U lambda? It'd be W times the lambda, right? W times the 5, correct? So the probability there's no occurrences from 0 to W will be 1 minus e to the negative lambda times W. Lambda again is mean number of occurrences per unit time. We've done this before, right? This is using symbols, but you did this in your last homework, didn't you? If you knew that there was 2 occurrences in a 12-hour time period on average, how many occurrences were there in a 24-hour time period? You had 2 per 12-hour period. How many would there be per 24-hour period? 4, right? You doubled it, correct? So all we're saying here is this lambda is number of occurrences per unit time, and W is the length of time. So we're just multiplying it, just like we did there. Yeah, Grace.
Where did the lambda to the x over x factorial go?
Okay, so no occurrences. So lambda to the 0 would be 1, and 0 factorial would be 1. That's where it's going here. And actually, technically, it's a good question. I'm glad you asked it. Seriously, this is your Poisson distribution would be e to the negative lambda x, lambda w, lambda w to the x over x factorial, right? Yeah, Michael. W is our variable, a little variable that we're using for our input for our random variable. So it's arbitrary for this particular problem. We're just picking a letter to denote that we're changing it to whatever we want it to be. So if it's 5, then W would be 5 in this case, and we would have 5 lambda in there. It's just whatever we're trying to say that our waiting time is less than or equal to. That's just the name that we're giving the random variable. But remember that the random variable is the function that changes whatever outcome we're looking to be an actual numeric quantity. That's all the W, the capital W represents. The little w is just a specific value that the function can take on. Okay. Yes?
So, like you said on the homework, when we were given a problem, we would give, say, 2 in 1 hour, and they calculate how many happen. If it was 2 hours, we just multiplied 2 to get our new mean.
Yep.
How's that different from this?
It's not.
It's not. Okay.
It's not. It's exactly the same. It's just that instead of using a 2 here, I'm using a W.
Okay.
Yeah. So the lambda is your occurrences per unit time, and I multiply by W. That it's W units of time.
Yeah.
So we're just multiplying.
Instead of just redefining lambda.
Yeah, it's just redefining a new lambda. That's exactly right. Yep. And it's just like the homework problems. We're just doing it with letters. I mean, it's literally just like what was on the homework problems. Okay. It's just changing the lambda. We don't have actual numbers here. Okay, so again, the difference between the capital W and the little w, the capital W represents the function that can take on all possible outcomes. That's what the random variable is. It's a representation of whatever the process is that we're doing. It's just that manifestation of outcomes change into mathematical notation, mathematical numbers. Okay? That's all the capital W is. The little w is a specific value that the capital W can take on. That's the difference between the two. I know it's confusing, and usually you can use them interchangeably. Because usually outcomes are numbers. So, like in this case, the outcome is a waiting time. So it is already automatically a number. I mean, you would strip the units off of it, but it is a number. That's the difference between the two things. I know it's a weird it's weird conceptually. Good news is you don't have to have 100% grasp on that concept to be able to do the problems. That's the big thing, is you don't have to have 100% grasp on what's going on with that concept behind the scenes to be able to do the problems. But that's what's going on. Okay. All right. Anyway, this now, so now we have, I'm just going to rewrite it down here. Now we have our cumulative distribution function in terms of little w. So what this tells me then is that the PDF of w is little f of w will be capital F of w prime, which will just be lambda e to the minus lambda w.
Is that the F on the big W?
It's a little w. The things that are the inputs in the functions are all little w's. The only place where there's a capital W is here and here. Those are the only two capital W's in the whole thing. That was interesting. I turned it to red and it changed this to red. That was really bizarre. Okay, anyway. Okay, so the first thing we're going to do here is I'm going to calculate the mean of this, only because when we get the mean, it's going to be in terms of the lambda, and we're actually going to flip around to the form of this PDF before I write down the actual definition of the exponential distribution. So you can memorize this if you want, but we're going to rewrite the form in a different fashion here in a second. You'll see why in a minute, I promise. Okay. All right. So let's say we wanted to find the mean. Well, remember again, the mean is expected value of x. So this is, remember, W is a waiting time. So what would be the smallest possible waiting time that you could ever possibly have?
0.
Be 0, right? So this will be integral from 0 to infinity. Oops, I wrote expected value of x, but really, I'm using w's here, so let me change that to a w. Well, I'm going to change it to an x in a minute anyway. It doesn't matter. The only reason why the book used the w to start with is because they wanted to do it as waiting time. So, as I teach my nieces, what does waiting start with? Waiting start with? W. There you go. Zaydin, yeah, you confuse them. So it'd be little w times lambda e to the minus lambda little w. Now you have to remember some calc too. What technique am I going to have to use? Oh, it's by parts. I know. Yeah. What's u equal to? Yeah, we did it last year. Oh, aren't you special, Grace?
That just confuses me. That's not okay. Gotta keep my things straight.
Then du is good. dv is
lambda e to the negative lambda w.
Okay, so then that makes v. That's a constant. I really don't want to do it again.
D is negative lambda.
And there's something that needs to be out in front.
Negative.
Yeah, it has to be negative to adjust, right? When I differentiate the exponent, the negative is going to come down in front, right? Okay, so our integration by parts formula says to do what?
du minus v. v minus u.
All right, so u times v minus the integral of v du. All right, oops, forgot my limits. So u times v will be evaluated from 0 to infinity, right? v du, it's minus the integral of v du, but there's a minus in front of the v, correct? So it changes it to a plus. Yes? Yeah? Right? When you do the integration by parts formula, there's a minus here. There's a minus in front of the other, so there's a plus. All right. This is more Calc 2, but I'm not going to go through all the details. W goes off to infinity. This goes off to infinity, but this goes to what? Well, this goes to negative infinity, but what does the whole thing go to? 1 over something getting really, really big gets really, really small, right? So it goes to, so I have infinity times 0, which is what? It's an indeterminate form, right? I would have to use L'Hopital's rule to do it. But which one's going to win? Let's just think about it this way. Which one goes to infinity faster? The e to a power, right? That's going to win, isn't it? Okay? So the denominator gets bigger faster than the numerator. So the whole thing's going to go to 0. Good. So when we put in infinity, we get 0. When we put in 0, we also get 0. So that completely goes away.
Wow.
Okay? That's why I said I'm not going to put in the details, right? That's Calc 2. You've done Calc 2. What are we all smirking at? Oh. Oh. All right. So now I need to do the antiderivative over here, but we've done this once, right? Okay. So I need an antiderivative for this. I gotta have a negative. I gotta eat into the negative lambda w, but now I don't have the lambda out in front anymore, do I? So I'm gonna need a negative 1 over lambda to adjust to this case, right? In the previous part when we did it, we had a lambda already out in front, right? This one we don't. Going from 0 to infinity. Again, when we put in infinity here, we're gonna get 0. So when we put in 0, we'll get 1 over lambda. All right, so let's think about the implication of this in terms of what the random variable is. I know, I want you to think. Holy crap, what am I thinking? I want to think about the implications of this in terms of the random variable. What was the random variable again? W. What was it representing? Waiting time, right? What was lambda again? Lambda was our parameter from our Poisson process, right? Representing mean number of occurrences per hour, right? So let's think of it this way. If you had, or per time unit, I shouldn't say per hour. But let's think of it this way. If you had 3 occurrences on average per hour, when would you expect the first one to happen? If you had 3 per hour, when would you expect the first one to happen? Yeah, in a third of an hour, or within 20 minutes, right? You'd expect 20 minutes, then 40 minutes, then 60 minutes, right? You kind of imagine it being, on average, equally spaced, right? Okay? Does it make sense that the waiting time and the mean number per unit time are reciprocals of each other?
Yes.
Yeah.
That's magical.
I know it makes sense, but it doesn't make sense. Where does the negative go away? What's that?
Minus a minus. Because when I put in 0, it's the second one I'm plugging in.
Oh.
So it makes it positive. That's where it went. All right, so to that end, this is why when we do the exponential distribution, we flip things around a little bit. All right, so the exponential distribution is about waiting time. So we're going to let x represent, I can spell the word represent, the time until first occurrence of whatever it is. Then the PDF of x is, we write it as 1 over theta e to the minus x over theta. So instead of putting the lambdas on top and then getting a mean that's a reciprocal, we start with the reciprocals. So the form for your exponential PDF is 1 over theta e to the minus x over theta. For some reason, theta is the parameter that's stuck. I don't know why. We know that waiting time has to be non-negative. Okay. So this gives us a distribution function of 1 minus e to the minus x over theta. the reason I know that already is because if I scroll back up, there was my distribution function, right? Here. And all we've done is just change out lambda for 1 over theta. Okay?
That's the derivative.
It's this way would be the derivative. Yeah. Yep. All right. And then we said the mean was theta then in that case, the 1 over the lambda. So whatever this parameter is in the denominator and in the denominator here, that's the mean waiting time. Okay? You can go through the same thing for the variance. You're going to have to do integration by parts twice when you do the expected value of x squared. So that's why I'm not doing it. Okay? It's not hard, it's just long. Turns out to be theta squared. Notice that this is probably the first spot where you might get a little bit confused in memorizing something. For Poisson, the mean and the variance were both lambda. For the exponential, it's not both theta. One's theta squared. So be careful of that. Okay? Yeah, Megan.
For this upcoming exam, is the exponential distribution on there?
Mm-hmm. Yeah, it's in your homework too.
Okay,
Yeah.
is it on the first cover?
Yep. It's on the right side instead of the left. It's the third one down.
Okay,
Yep.
so you need all those two.
No, just the uniform and the exponential. Not all of them. Just those two. Uniform and exponential. That's it. We'll do the other ones after the exam.
Those are the only two we need to know.
And all the discrete.
We need to know uniform.
Those are the only two continuous ones that you need to know. for
Well, I
the
just
exam.
mean for that first question, front cover question.
You need to know all the discrete ones plus
Okay.
those two continuous
And
ones.
those are the ones that are written on it.
Correct.
So all I want to know.
Yes.
Is there gonna be a question that's like, what is this equation?
There's going to be a question that's going to say, literally going to be, fill in the blanks for these distributions. And they'll say, you'll have hypergeometric, and you'll write the PDF and write the mean. And write, yeah.
We have to write the moment generating function.
Say that again?
The moment generating
Yeah, for some of them, yes.
The k minus something.
Yeah. Some of them don't have moment generating functions written down, so you wouldn't have to do it for those.
Bless you.
This page,
That's an angry
the uniform and the exponential.
We have to know both uniforms.
Yeah. There's a discrete uniform and there's a continuous uniform. You need to know both of
Know
them.
when to use which one.
Well, yeah.
Try don't.
Yeah.
Less.
Bless you.
Less.
I mean, it's not going to be a surprise when you see the exam. There's going to be fill in the blank for the first question.
That should be the whole test.
Yeah.
No. 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 Why would that be the first question? Or the only question, I mean.
Because it tests our knowledge.
Have you wrote the test right?
No. I've written tests over this before, but not that test yet. Okay. All right. What's that? What was that? I didn't hear what you said.
I was saying make this one easier than the last one, right?
That's
Your
funny.
tests are hard.
All right. What's that?
So they are. She said they're hard.
Your
So they
tests
are.
are hard.
And?
You don't pull any punches.
I mean,
Dr. Joe, you're bullying us.
that's right. I give partial credit.
There's been a live seal of approval on test difficulty, and that's not a good thing.
Of course they're hard. What would be the point of it? They were hard.
You take one.
Yeah.
No, take
Don't make it harder.
I'm not going to make it any harder because people are whining. If I did that, it'd be impossible.
So if we don't whine, it'll make it easier.
No. The level of difficulty of the exam is independent of level of whining. To use a probability joke. Independent of. Ha 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 ha! Gosh. Would you like me to do some problems? What's that? We can probably have pizza in here too.
Oh, man. Different days though.
What?
No, same days.
It has to be the same day. There's too much overlap.
The probability baskets of leftover theory.
There ain't gonna be no leftovers
Pizza, if we're
if
getting
you don't
pizza on
have
both
it.
classes,
Yeah.
we shouldn't get pizza on the same day.
So what you're saying is that you should have. Okay, I got you.
Well, I'm doing twice the amount of work because I'm in both classes.
You want twice the amount of pizza.
Yeah.
Oh, I got you.
Makes sense.
That makes sense.
It was like a worker.
When's our next speech party for EMS studies class?
At this point, it's probably going to be advising day.
Is what?
Advising day.
That's sometime in November, right?
November 5th, I think.
So we're not that far. Less than a month.
I'm excited.
All right, let's look at 3.4-6.
Okay.
So this one's set up as just telling you that x is an exponential random variable with mean 20. The first part A asks you to find the probability that x is between 10 and 30. All right. So the first thing you're going to need to know is what the theta has to be. Because for an exponential distribution, just like you had a Poisson distribution, you need to know what to plug in for the parameter, correct? The exponential distribution has a parameter. That parameter is theta, correct? So if the mean is 20, what's theta? 20, right? So mean 20 tells us that theta is 20. Good. Now, there's a couple of ways to get at this particular answer. There's one way that's easier than the other. The reason for that is you typically think of doing probabilities for continuous distributions by doing an integral, right? We talked about this before. We would say, if we were just not even thinking, the way we would do this is we would integrate the PDF from 10 to 30. Right? We agree? Okay. And you can do that. There's nothing wrong with doing that. You can take your PDF, which in this case would be 1 over 20, e to the minus x over 20, right? And integrate it from 10 to 30. That's certainly one approach, correct? Okay? But notice that we could also rewrite this in terms of the cumulative distribution function, right? Remember we talked about this where I had my hand over the screen and people couldn't read 3 inches above my hand, right? How can I rewrite this probability in terms of the distribution function? Right, I do the cumulative distribution at the right endpoint minus the cumulative distribution function at the left endpoint. By the way, for continuous functions, this is essentially the fundamental theorem of calculus. Oh my God, another thing with the class before this one that came into this class. This is the fundamental theorem of calculus. Your cumulative distribution function is an antiderivative of your PDF. So to evaluate the definite integral, we plug in the endpoints to the antiderivative. Like I said, this is another calculus concept, right? Okay. So if I know the cumulative distribution function, I could do this easily. Well, do I know the cumulative distribution function for the exponential?
Yeah.
Yeah, we do. It's right up there, isn't it?
Wow.
Right? Okay. It's a magic moment. One shining moment. Right. All right. So in this case, it would be 1 minus e to what power?
Negative. Over.
Good. Yep. Yeah. So the cumulative distribution function is e to the minus x over theta, right? The x in this case is 30. The theta was 20. So that's our input here for the cumulative distribution function. Because I haven't done the second part yet. I'm doing out of 30 right now. Yeah. So then I need to subtract off. What do I get when I plug in 10? Yeah. 1 minus e to the negative 10 over 20. So this is going to be e to the negative half minus e to the negative 3/2. If you simplify. Which didn't involve any integration at all because the cumulative distribution function already took care of the integration, right? So I didn't have to do anything crazy with the integration. Let's do part C here. I'm fine with that. Do you really want to do anything with it?
Well, I mean, my calculator was nice, but I had it ready with that.
If you,
Are we
unless you're doing something that has the multiple choice answers and you want to check it against it, that's a perfectly acceptable answer.
0.38.
Okay. I mean, it doesn't hurt to type in your calculator and make sure you have something between 0 and 1 since it's a probability.
We do. We don't worry.
How about we do the probability that x is greater than 40 given that x is greater than 10? Oh, I know, conditional. I feel bad. I gave you a conditional.
Do you know?
No. All right.
The probability that x is greater than 40 intersect x is greater than 10, and the probability that x is greater than 10.
Good. Good. We can combine it as what, Megan? Combine it as what? You're right.
It can just be x is greater than 4.
Good. Say again why?
Because, well, that also includes x is greater than 10.
Fantastic. That's exactly right. Good. Yeah, that's exactly right, right? The x being greater than 40 automatically guarantees that x is greater than 10, right? So I can just do x is greater than 40. That's fantastic. Good. Excellent. Can I rephrase these now in terms of the cumulative distribution function? Probably, or I wouldn't have asked, right? I have to do the complement. Good. So what would the complement be?
1 minus probability that x is less than or equal to 40.
Good.
Wow. We are really killing this, guys.
I hope he puts one on the test.
You're welcome.
Yeah,
Why
Morgan.
do we have to write it as a complement?
Because remember, your cumulative distribution function is, by definition, up until a certain point, as opposed to beyond a certain point. Okay. So using our cumulative distribution function now, what am I going to put in the parentheses here?
1 minus baby size.
We are.
To the power of negative.
Okay. And on bottom?
1 minus e to the negative 10.
Okay. Notice that when we've got this complement idea, I've got 1 minus and then a 1 minus again, right? So notice those will just end up canceling each other out, and we get e to the negative 2 on top and e to the negative half on bottom. And if you're really feeling fancy, that's e to the negative 3 halves.
Oh, man.
Subtract your exponents. Is this okay?
Yeah.
Yeah, Sam?
So was this part B?
This is part C. I skipped B.
You're not going to be.
I was looking at the time. People told me I let them out too late the other day. Not
I
looking
just
at
said I needed to get out on time today. You sometimes go over.
I do. I know. I was trying to be cognizant of the time. I got chewed out last hour, so. All right. So one last thing to mention real quick is the moment generating function, because sometimes you'll be asked about that. You can derive it. It's not hard to derive. For the exponential, it's just 1 over theta t. So in particular, one of the things that you can notice from the moment generating function for the exponential, if you're given the moment generating function, you're automatically given the mean. It's the coefficient on the t. Okay? So, anyway, we'll talk about stuff for the exam next time. Otherwise, have a good weekend. We'll see you on Monday.